constant. The density does not change in the liquid, not enough to be affecting. That will not be the case in gas phase, but right now in liquid phase, that's true.
Yay, liquid phase.
What else did I find? Oh, read what's really asked of you in the question. There was only one question you actually had to give an answer to. The rest were just derived on mass balance. At least one person lost points because they gave me an answer that wasn't asked for and they gave me the wrong answer. For Dr. Jennings, if you try to do extra and it's wrong, you lose points for that. If you just have to derive equations, just derive the equation. Giving the answer is not going to give you extra points or anything.
Some people feel doing numbers makes the problem easier, helps them understand it.
Then you are not understanding the concept of what you're doing. You're purely trying to model a system. Who cares what the actual numbers come out to be? Try to talk about this in the chemistry class I teach. I give them an answer at 1.2 and they're like, but I got 1.3. Does it really matter?
No,
There's error intrinsically in it. Can you model it properly? Can you write a meaningful equation out of thin air? Can you do that? If you can do that, then who cares about doing the algebra? Doesn't make any difference at that point. You get paid to write the equation, not to solve it. Or you don't get paid as much as all you to solve the equation. You get paid more if you can write it. Well, I'm looking at the next homework. So I'll give you some stuff that'll help you out with this. One thing I can already tell by reading the first problem is you're going to have to use this. You're going to have to use this constantly. So if you substitute in an equation, such as you know that if you're in a mixed flow reactor, you don't have any derivatives or integrals to deal with, just an algebraic expression. If you have an expression like that, you can sub in for any three of these variables, right? By just rearranging them, you can say, if you want to write FA in terms of FA naught and XA, you can just throw that in there instead. What if you have this? You want to sub in for FA right there.
is that like derivative?
Yep.
Okay.
You just throw in this FA equals that and put the D in front of it. You can't do that. You have to actually go and derive it. So really, what you would end up doing, you'll see this quite often. Number 2, I think you have to solve it this way, but either way, we're gonna have to do a bunch of it. So if you want to integrate in terms of your conversion, such that you end up with this dxa over dv. If you want to change a variable, look that up in a textbook if you need better instruction. But if you want to do a change in variable, then you simply take the derivative of what you're trying to sub for with respect to what you are going to sub it with. If that makes sense. Either way. So first you need the equation that has both of the variables in there, otherwise you couldn't do a substitution anyways. But then you take the derivative of what you're subbing for, FA, and now you have DFA, you have DFA here. You want it DXA to go right in there. So take the derivative of that with respect to XA. What's the derivative of that with respect to XA? Negative FA naught. Right? This equals FA naught minus FA naught XA. What's the derivative of a constant? What's the derivative of this with respect to XA? Minus FA naught. So you would get d FA dXA equals minus FA naught, or d FA equals minus FA naught dXA. Right? So now, when you come to this guy, you will just say dFA dV equals minus FA naught dXA dV. You substituted this in for that. Change a variable.
I remember that.
Could happen all the time. Gonna do a lot of that. So you're gonna do that quite often. So when you see in his solutions, or if he goes through an example, you just see this on one line where it's dFA dV equals something something something. Next line you see minus FA naught dXA dV equals something something something. You'll know where that negative at FA naught came from. Came from the derivative of this equation, or the derivative of FA represented by this equation with respect to XA. So you're going to do that a bunch. I'm pretty sure on problem number 2, you're going to have to do, I'm sorry, problem number 1, because you were given conversion, you were not given anything in terms of your flow rate. All you know is the volume, you know your reaction time, and you know your conversion. That's all you know, right? So from those, you're going to have to get rid and cancel out number of moles, because it does say batch reactor, right? What do you think you're looking for in that first problem? Has anybody even looked at the homework yet? Yeah, I have solutions for the same problem right here. So I'm just going to solve them both. One is a CSDR and one is a plug flow. Show you the differences. So your reaction is A going to B. It's first order. Our rate then is defined as minus KCA. Your rate, A is being consumed, it'll be a negative term there. That negative is up to you whether you want to put it in right there or you want to put it in later. Volumetric flow rate is 10 liters per minute. Rate constant, 0.23 minutes, and CA equals 0.1 CA naught. So we want to find what the reactor volume required to solve, to have this reaction take place. Really, we want the reactor volume that will satisfy that condition. That means when you go into the reactor, you have your initial concentration of A. You've spent enough time in the reactor that it's reduced by 90%. You only have 10% left in it. Yeah.
So units on K, is that per minute?
Per minute. First order is 1 over time. Second order will be the inverse of concentration over time, so forth.
So if we see a concentration like that, do we have a conversion factor as well, potentially? Okay, so we can just say X is equal to 90% conversion?
Yeah. Good. Let's see if I can solve this a couple different ways for you. But, as always, first, start with the material balance, basically from scratch. FA naught, what comes in minus what goes out, plus whatever your accumulation or your consumption is. In this case, you're consuming A, so it's what am I doing? Oh, rather nasty cold, as I'm still getting over. Pretty hopped up on medicine right now, so find my mistakes. They will be all over the place. This comes down to notation. I just want to talk about this. I wrote this as a positive right here. But look how I have rate of A defined over there. It's negative KCA. So this is actually a negative term. You wanted to, you could have left this as kind of an absolute value. It's the rate of A. producing A or consuming A. I don't know much about it. This is what goes in. This is what comes out. This is your consumption or production term. So it's either positive or negative. In this case, I could have said that. I know I'm consuming A, so it's a negative rate of A on that side. But it's just however you want to understand it. You decide where you want to put your signs and how you want to deal with them. But that's just something you're going to have to figure out on yourself. So that's your generation consumption term. This is your accumulation term. This for a long time is always going to be 0 because we aren't going to do anything that's not steady state. I don't think we ever do anything that's not steady state. Maybe set up a problem one time. You start getting nasty when you do that stuff. So still, you have your equation here. You're a mixed flow reactor, so you're just having an algebraic expression. You can't do a differential on the finite values along the reactor, so you can only do the inlet and what's coming out. So it just remains as an algebraic expression. I think most of the time you're going to see it in this form. I know he writes it that way a lot. Leave it that way if you really want to. If you write it this way, it looks a lot like it does for the plug flow reactor, which is going to be. But notice positive here, negative there. So we'll talk about that in a second. But at least in these forms, it's the same. The units are the same for the numerator and denominator and your rate term. So I guess that's why it does it that way. I'm not really sure. So the big problem here is that we have not commented at all on the flow of A. We have no idea what FA is. We don't know the volume because we're trying to solve for the volume. I guess I can put that there. What is the volume in this problem? The rate we know a little bit about. We know our rate constant, and we also know what our final concentration CA is going to be in this. So that's good information to have. We don't know exactly what either one of those are, but we have a ratio of the two together. So that's all the kind of stuff that we're going to have to tackle. Really, like I told people before, this is nothing more than a linear algebra class. One equation right here. How many unknowns do I have in this equation? I don't know you. I don't know you. I don't know you. I don't know you. I don't know anything in that equation right there. We need more equations. So you start chipping away at it, coming up with other equations for it. Let's start with the rate because that's an easy one. So let's tackle this guy right here. So RA we know equals K times CA. We know that because it said it was a first order reaction. Even if you didn't know that, the rate constant here is given in terms of first order. It's 1 over time. The only logical way to express the rate is going to be K times CA. It's the only way you can comment on that guy right there. So you can plug that directly into here if you want. I don't want to do that quite yet. I just want to write down a couple more equations. So what do we know about, let's start with FA naught. What equations can we write on FA naught that could potentially be useful?
QC naught.
Yeah, not Q naught, not Q initial, Q. We're liquid phase right now. So Q is constant. Q times C naught equals FA naught. Same way with FA equals Q times CA. Let's plug all that stuff in now. Let's plug in these 3 equations, see what we come up with. Let's just move it over here. So for FA naught, it was Q, CA naught minus Q, CA divided by V equals K, CA. How many unknowns do we have now? We don't know you, we don't know you, we don't know you. We just knocked out half of our unknowns right there with 3 equations. We don't know CA naught, we don't know CA. relationship between the two, but you do not know what CA or CA not equal. You do not know what those equal. Let's use a given equation, plug in for either one of those. Let's see which one I did so I don't get off track too much here. Which one did I plug in for? Looks like I used CA naught because it's already expressed that way. So everywhere you see a CA, put in this expression. I'm gonna go ahead and clean this up a little bit. Q, I have CA naught minus CA naught times 0.1. That's where CA was right here. Divided by V equal K times CA naught times 0.1. Can everybody follow this if I just do this? Does anybody not understand how I was able to just cancel out all three of those CA naughts like that? Just algebra. Divide this CA naught right here, cancels out with those guys. So what are you left with? You just have Q. Let's just separate everything the way we need it. Q over K times 1 minus 0.1 will equal V. You know this, that's just a number. Solve for V. It's a linear algebra problem. How many more equations do I have to come up with to solve that thing? I had 4 unknowns. Don't know you, don't know you, don't know you, don't know you. How many more equations did I need? 4. 4 equations. The CA equals 0.1 CA naught. Equations. There you go.
Are you missing the point one?
Yeah, what happened to the other point one?
What happened to what?
Point
Oh,
one.
yeah, the point 1 should be there too. Chalk that up to Dayquil. Stuff hops you up pretty good. There you go. So, pretty simple overall. The key here is that this, in the generic form, if you see me box an equation, I would try to burn that into your memory as best as you can. That's an important equation that's going to be useful throughout the semester for you, at least in liquid phase. That equation will not work in gas phase, as you'll see later, because well, that's not even talk about it. Let's get this nailed down first before we screw everything up. So if you plug in everything, if you want to go through and solve that later on, you should end up with 391 liters, in case you want to go and solve that yourself. Once again, I could care less about what the number comes out to be. You set up the equation, you go home and finish that if you want. But what do we still need? Well, let's do it as a plug flow reactor. Let's see. Should we TQ? I guess we no, let me knock this out. There are a couple other people, so let me talk about the plug flow reactor again real quick. Let's just start from the beginning. But keep it in your mind, it's about 400 liters in a mixed flow reactor. So you'll get a different level in the plug flow reactor. So the mixed flow reactor, it's a simple algebraic expression, in, out, plus or minus your generation, consumption equals your accumulation. It's just an algebraic expression. For a plug flow reactor, there's some long reactor here, it has some kind of laminar flow going through it. All that. So, since you have your laminar flow, nothing in the front of reactor can jump all the way to the end and then come back to the beginning and things of that nature. If you have a mixed flow, you have an inlet right here, an outlet over here. If you did a trace of a particle, you could come in, you could come to the exit, you could go just all over the place, and then you finally make it out. You could just do a straight line in and out of it. You have no idea in terms of concentration and position in the reactor. You just know what this concentration is and that concentration is. Plug flow reactor, you can figure out what the concentration is at every single point in the reactor. So if we just take the difference between these 2 points. Call this, some differential volume. That's volume right there. This is V plus dV. At some point, volume V. This distance is dV, so this is V plus dV right here. Inside of this right here, you have a reaction taking place, RA. So let's go ahead and write that thing out the same way we did the other one. You have what's going in, so you have your flow rate A at V minus your flow rate of A at V plus dV. And then you have plus your reaction times the volume dV. Just say we're in steady state, so it all equals 0. This basically we're going to the definition of a derivative here. But if you take all of this, multiply it by -1 over dV, then you're going to end up with FA at V plus dV minus FA at V divided by dV. Minus RA becomes plus RA equals 0. This right here, if you remember from calculus, that's the definition of it. Take the RA to the other side, equals minus RA. It's your equation for your plug flow reactor. It's just the definition of a derivative. So now you don't have to memorize those things. You don't have to memorize that dFA over dV equals negative RA. Mixed flow reactor is FA naught minus FA divided by V equals RA, whatever else. You just derive it, simple. So that's where you get that equation from. So we'll see if we have to show that one. One more. So if we do the exact same problem, we're going to end up with definitely a different answer, but we're also going to solve it a little bit differently. So if we start off with our equation, I just derive dFA dV equals minus RA. How many unknowns do we have in there? Do you know volume?
No.
Do you know FA?
No.
Do you know RA?
No.
At least 3 unknowns right now. Truthfully, I don't even care if you count your unknown, you know, how many equations do I need? That's not important. Identify what you know and what you don't know. What you don't know, write an equation for it, and then reevaluate it again. Chances are you're not going to know something in that equation. You might have to write another equation, but just as long as you follow that route, it'll work for you. So let's start with FA. In this case, we could do it either way. We could do it in terms of conversion, or we could just do CA. Let's just do CA, because I think that's how I solved it here. I'll do it both ways, just so you can see that there's more than one ways to solve these things. So, once again, the important equation. Liquid phase, FA equals Q, CA. Do we want to try to calculate anything with FA? It'd be a lot better to do it in terms of CA, because we already have an equation with CA. Let's do a change of variable from FA to CA. DFA, DCA, do the derivative of this guy with respect to CA. What does it equal? Q. This equals Q. So DFA, DCA equals Q. DFA equals Q, DCA. That was a lucky one. You could have just plugged the 2 in and got away with it. If you do XA, you won't get away with it doing that. So we can say that this equals Q, DCA, dV equals minus RA, and I'm just going to put in KCA. Put that in there just like that. What do we not know in that? Or V, for that matter.
Yeah.
But we don't equations do I have to use? Do I have any other equations to use right now?
Integrated and C over C.
Yeah, if you run out of equations, try something. Let's integrate it. So, let's say we have ECA over CA, we're gonna integrate that from CA naught to CA. Better yet. And I'll just leave it right there. That's fine. Let's take K over Q, dV. K and Q are constants. From 0 to V, the beginning of the reactor, you have no volume. Go ahead and solve those. What don't we know in this equation?
CA, like.
We don't know CA. We don't know CA now. And we don't know V. We have three unknowns in this equation. We do not know this value. We do not know that value. We do not know V. Now we have one equation and three unknowns again. Thankfully enough, we're solving for one of the unknowns.
That's not negative K.
Yeah.
Here, why don't I do that instead? I can do that too, couldn't I? It doesn't have the pass. I'll leave the negative one. So you have C naught over CA. You use this equation right here.
Isn't
no,
that,
it's right.
doesn't that make a, like,
Wait,
you can combine the two?
I can do that, can I? That in there. Those are gone. Only thing you don't know is this volume to solve for it. It's linear algebra. This only comes with practice. Practice beyond just the homeworks it gives you because, well, those just are tough to solve. They're not easy. So, I'd say both of them were kind of a pain in the butt. Let me solve this another way. So based off this right here, what's the definition of CA naught? CA naught equals, or CA equals CA naught times 1 minus XA, right? Which comes from the fact that CA equals, what was the base equation for this guy? I'm always used to writing it that way. We go back and look for it. My brain is slowly shutting down. Where was it? Oh. Yeah. Yeah, you could get it directly from this, or you get it from the fact that XA equals 1 minus CA over CA naught. Both say the exact same thing, they're just rearranged. One of those two you kind of just got to memorize, whichever one of those two. But one of them you're going to have to hold on to and realize that you can rearrange them to solve for any of the three. This is a very powerful equation. This relates three different variables together for you. That's one you're going to need. This deserves a box around it. Or that one, whichever one makes more sense that you can remember in your head. Keep one of those two equations stuck away there. So, using this equation and putting this guy in there, I got CA equals 0.1. Oops, this guy. 0.1 CA naught equals CA naught 1 minus XA. Those cancel out so that 0.9 has to equal XA, right? You could do that step first if you wanted to. I took this equation, I plugged this into it. Where CA is, I put 0.1 CA naught. Both of them have have a CA naught right there, I canceled them out. And I went ahead and did the algebra. 1 minus XA equals 0.1. XA has to equal 0.9, right? So now we have this fact, which is telling us the exact same thing as that, which you pointed out. It was telling us the exact same thing. We can do it from this part now. DFA dV equals minus RA. Same thing, we have unknown variables we have to deal with. Let me go ahead and put this in here. KCA. So there's an equation right there for CA. I can plug in if I wanted to. I can use that. Let's see if we're going to want to use that or not. We'll wait and see. So let's go ahead and do that. We have our unknowns. We don't know FA. We don't know V. We don't know CA. We do know XA, and here's an equation with XA. So let's throw that in there. Negative K C naught times 1 minus XA. Throw that in there, right? No big deal. I just took this, used this equation, put it right there. So I know you, I don't know you, I know you, I don't know you. Oh, well, you're gone now. I don't know you and I don't know you, but you're what I'm solving for, so I'm not that worried about it. FA. What was the original equation that I wrote for FA? FA equals FA naught times 1 minus XA, right? Let's expand, don't want to expand this thing now. No, let's do it right now. Need to do the change of variable. We need to change from DFA to DXA. Whatever variable you're going to change it to, just divide by that variable. Take your equation, take the derivative. Equals minus FA naught. We just did that a little while ago. So you get minus FA naught. Get a change of variable from this guy. We took the derivative of this equation with respect to XA. We get minus FA naught right there. Take this, move it over to the other side. Now we know that DFA equals minus FA naught DXA. We can put that in right there. Let's do that. Minus FA naught DXA dV equals negative K CA naught 1 minus XA. Negative signs go away. And negative signs on both sides there. What don't we know now? Don't know you. We don't know you. How would I handle that? Somebody tell me how to figure that out.
FA naught equals
Change
Q
this.
C naught.
Gotta go back to another equation. FA, in this case, we're talking about FA naught, so I can write it in terms of that. We equal Q C naught. You know everything on there. Just integrate it. There you go. This way is a little bit longer than the other way, isn't it? Not too much longer, but it's definitely longer. Still, it's going to give you the exact same answer for V. You're not going to get a different answer for V, but two completely different ways to solve the problem. One, if you've done a lot of them, you would stick with this method because you're already given CA and you can integrate this with respect to CA. Or you could use that to find XA, and then you have to still use that same relationship, and you have to use this guy, and still gotta do the change of variables to get this expression. And that's a tougher integral too. What is that? Is that negative ln of 1, negative ln of 0.9 over 1, negative ln of 0.9, is that what that is? Anybody know? That's an integral you probably need to memorize for the test, if you want to solve the problem all the way to the end. If you get this far, you're probably good enough. Just right, don't remember the integral in there. Any questions? Is this like, oh gosh, this is a lot? This is like a test question, exactly what you're gonna see. So, be prepared to have to solve that all the way through. Could be more difficult than that too, I don't know. That's only liquid phase. Gas phase is just gonna be one more layer of complication on top of it. Anybody wants to solve this all the way through, you should get 100 liters. You have a plug flow, only takes 100 liters. You have a mixed flow, it took 400 liters. Should always go with plug flow, right?
No.
I guess for the other people who are here for the first time too, these are two ideal scenarios. You either have a perfectly mixed flow reactor or a perfect plug flow reactor. In real life, it's a combination of the two. And if you keep on going further in reactors, you'll read how you model both systems simultaneously by doing them, you know about doing them in series and in parallel, the reactors in series and stuff. You'll do a plug flow and mixed flow in series or in parallel to model what a real reactor is actually doing. But you base it off these two idealities here. One is purely plug flow, the other one's purely mixed flow. Just how far along the spectrum really is it? That's what your model will have to figure out between the two. What in this is confusing? Hmm?
Joking.
I don't know what to say, but okay. Any part of this confusing?
I just have to remember to change the variable.
Just do a couple of them, it's easy to do.
Yeah.
Change of variable is really simple to do.
Yeah.
What variable did you start with? What variable do you want to change it to? You just need an equation that relates these two variables together. Change a variable, take a derivative of it. Not hard to do. What else do I got here? Is this the same thing? Is it CA squared? Okay, how about we do the same thing for this problem. Both scenarios. Oh, did we pass around the sheet for everybody to sign? Did we do that? We need to do that.
I just started a sheet.
Yeah, make sure whatever that sheet is, you get your name on it.
No, it's everybody.
What's the reasoning behind that?
Statistics.
Is that extra credit?
Okay, you wanna know if it's extra credit or not? This is the difference it'll make. Right here I have last year's people that attended tutoring and didn't. So, there was a total of, I guess, 13 sessions, because that's the highest number I got here. So, I'll go through all the D's and the F's first. Only attended one session. D, D, C, D, D. 3 sessions got a D. 1 session got an F. 1 session got a C. 5 sessions got a D. It's not for everybody. 7 sessions got a D. 1 session got a D. 1 session got a D.
You have 0 sessions.
Well, I wouldn't have their name on here if there were only 0 sessions.
So that one.
1 withdrew. 2 sessions a C, 1 session a C. Somebody attended 8 sessions and they got a C. 3 3 people attended 6 times, they all got A's. 1 person attended 7 times, they got an A. 1 person attended all 13, they got an A. 1 person attended 13 times, they got a B. Another person attended 13 times, they got a B. 2 other people attended 10 times, they both got A's. Couple of the outliers, 1 person attended 5 times, they got a B. 1 person attended 7 times, he got an A. So, there's your extra credit. You show up, you get a good grade. If you pay attention. It's intrinsically built in. Besides, some people can't come to this, which is unfortunate for them. But, same thing I told everybody last class, and I told Dr. Jennings, and not a first person's contacted me yet. I'm willing to do this some other time, but it'll be their responsibility to contact me. I'm not gonna figure out a time and say, okay, you guys can come this time. I'd rather just not do it. But if somebody asks me, I'll do it, especially if you need more than just recordings or talks. But here's to hoping nobody contacts me. I can have it on my Saturday, so. It'll probably be on the Saturday.
Your midnight call?
Nothing about
Yes.
that.
Yeah, that makes sense.
Only on
Yours made
midnight
no
to
sense.
keep honest babies.
Yeah, that would be cool.
I'm not sure if I can take that many consecutive hours of reactors though. 30-minute break is really nice.
Okay. This one, liquid phase. 2A going to group B. Uh-oh, why does it say that? Oh, okay, fine.
What does it say in front of the 2A goes to B?
Liquid,
Oh, okay.
LIQ for liquid phase. Do, pure A in the feed. Q equals 25 liters per second. C naught equals 0.2 moles per liter. K equals 10 liters per mole per second. What's the volume? Solve it for a CSTR and solve it for a plug flow reactor.
CT, is that CT or?
I don't know.
Like
C-
2.2?
CA naught, CA naught.
Okay.
First of all, what order is this reaction? How do you know it's second order?
Units on K.
Units on K. Do not look at this and assume it's second order. Although it kind of tells you it is. That's the units for a second order reaction. If it's a second order reaction, then it has to be the rate of A has to equal K CA squared. That's the only reactant you have is A. So that's one of the things you have to pick up on it. KCA squared is the rate. So if we go through and, oh, I'm sorry. Conversion, we can give you that.
Isn't it, oh, yeah.
That's the volume if you have conversion of 90%. So if you do it first as a CSTR or a mixed flow reactor, whatever you would call them. What do we do here? Where do things like say? Okay, that's fine. First, write your material balance. You get that right there.
Is this mixed flow or plug flow?
Mixed flow, CSTR, mixed flow. Here is an instance where the sign convention is gonna be important here. Notice that I didn't put a negative sign here. There is no negative sign right here, either. And that is, did I write with a negative sign in here? I'm looking at it.
But you're doing it in terms of the product, I mean, you're doing the rate in
Well,
terms
it's a
of A,
negative
so
and it's a
it is
negative term, so it
decreasing.
still should be positive that way. Yeah, it's still the same way it should be. But this is where reasoning is gonna help you with the sign convention of things. Okay, you know you're going from A to B. greater than or less than FA? It's greater than, so this is positive. Volume has to be positive. This has to be a positive term. Just reason it. Think about it before you try to memorize, oh, is it positive or negative right there? Just reason it out.
Oh, I see.
Just reason out what you want to do with it. Let me just go ahead and talk about this one. DFA, dV equals minus RA. What do you take when you take the integral of something? Final minus initial. The final state of FA is less than the initial state. This is a negative term right here. Final minus initial right here. Your final volume is greater than your initial volume. Positive. This is a negative term. This has to be negative. Just think about those things for a second. Don't try to memorize equations. Understand what it is they're saying, and then you can reason out what the signs need to be. Just like reading a sentence. This is a sentence. You just have to understand the grammar of it. Lack of a better analogy. Noodle is a horrible analogy. I hate grammar. So, I don't want to solve this all. I just don't want to do it. Okay, so, what variables do we not know?
FA not, FA, alright.
You don't know anything. No, it's good. You have to identify that you don't know any of these things. You do not know any of these things.
FA not equals CA not times Q.
Okay. That's one of them we'll use. But still, you need to look at this equation. It's just like anything else you do. You don't just go into trying to fix something without reading the manual first. Or you don't start putting something together and then halfway through start reading the manual. I mean, there's a certain procedure going through it. First procedure in this, what do I not know in this? I don't know any of these. So I'm gonna have to factor every single one of those. Just identify that first really quick before you start subbing things in. It's just gonna make your life a little bit easier. Of course, it just comes with practice. Just like anything else, like, oh, I got these down, let me just start putting this in here, and the next thing you're like, wait a second, things aren't working out right. Maybe you forgot it's about something you knew or something you didn't know. So, don't know FA. What do we know about FA that's possibly up here? Q, CA naught, that's FA naught. We know that FA naught equals CA naught times Q. We know both of those too. We also know that FA equals CA times Q. We know both of those. Do I know CA?
No.
No? Okay, we'll deal with that in a second. RA, we know is gonna be K CA squared. Oh, twice we don't know what CA is. Volume, that's what we're asked to solve for, so. That is our final equation. V equals something and all of our knowns. That's the final equation we're trying to get to. So what else do we have that'll relate something to CA? Up there, what is something we have that will relate CA to something else?
Conversion.
XA. Write an equation that relates CA to XA. What do we know? CA equals CA naught 1 minus XA. I think I've accounted for everything. Let's plug stuff in. Let's just write a couple things. All that stuff there, right?
You can also just,
I don't wanna do a ton of steps all the way to the end, but I think that's enough. I can say that Q times CA, and I group those together. I said CA right here equals that. I'm about to do the same with this guy right here. So let's do that real quick. Q over V. And what's Q over V?
Space.
Space-time. CA naught minus CA naught times 1 minus XA. And V's already right there, and then equals A times CA naught 1 minus XA. I wrote this out because people.
Square.
Oh, yeah, this is all squared. Sorry. I wrote this out right here because
wouldn't it be easier just
stuff right here. So take the time, at least a few, to write this all the way out. Write that all the way out so you see that this just becomes Q over V times C naught XA. Please take the time to make sure you get that. I see the strangest stuff pop up for what should be a very simple. Separate all these. That goes away. What's the only thing you don't know there? Only thing you don't know is V. We got Q, we got XA, we got K, we got CA naught, we got XA. The thing I know is V. Separated everything and solved the problem. $11.25 liters, if you want the answer. Rearrange it for V. What if we have to do it for a plug flow reactor? Let's see what it comes out to. So, we got PSA. Identify what you don't know. I don't know you. I don't know you. So what do I know? I know RA equals KCA squared. And I know that DFA XA, because I have XA here. I can do it with CA if they gave me the final concentration CA, but I can still do that too by taking CA naught and working with conversion. I don't know if you really want me to solve it that way too, I can just to show you, but so this, I should have written this out first. No, I don't do it that way. I just make this go all the way. Let's just do it that way. I'm gonna write that all the way out like that. Which Q times, this is FA naught, right? Right there. I'm just gonna write it all the way out this way. FA naught equals Q times CA naught. I'm gonna take one big leap, put that there. Because FA naught equals Q times CA naught. So, DXA is gonna equal negative Q CA naught. So plug that in for it. This negative sign is going to cancel out with that negative sign. Use CA naught, DXA, dV equals K, CA squared. What does CA equal? Used it before. point, these things get so messy that you have to use some kind of solver to do it. You'll end up with like a 12 by 12 matrix. Who wants to break down a 12 by 12 matrix by hand? It's a pain in the butt. So just plug it into polymath. Polymath's just a linear algebra solver. So you can do differential equations. It's not magic. There's nothing magical about it.
But if I don't know the exact math way how it works, then you just say it's like the black box.
Guess I can do a batch problem since I think there's a question about one here.
Excuse me.
Yeah.
I just want to make sure, how did you consider the CA initially?
Why don't you go over here and point to what you're talking about?
The last one, the last.
Right here?
Yes,
How did I do what?
you cancel it out,
This guy?
yeah.
Because this is squared.
Oh, okay.
So now this is to the first power, and that no longer exists. Q over V times XA equals K CA naught times 1 minus XA squared.
Oh, okay, okay.
This squared is now
Yeah,
gone,
Okay, okay,
and this is gone.
all right.
You don't have any
The
badges?
material balance for a batch reactor?
Yeah, no in, no out, so it's just the accumulation. Right?
Yeah, a batch reactor doesn't have an inlet or an outlet. You throw stuff in there, it reacts,
So basically, it's just.
so it has an accumulation term.
Basically,
It has to, or else no reaction's taking place anyways. Let's see here. So, for a batch reactor, what goes in? Blue.
CA naught is A.
Both zero. Nothing goes in, nothing comes out. You still have a rate taking place. You have to multiply that by the volume. I think I missed that on the material balance for the mixed flow reactor. You have to multiply it by volume. So this is your gen consumption. And because nothing's going in and out, if you're generating or consuming something, you have to accumulate. Number of moles of A per time, I guess I should use the capital A. So if you just look at the units, your rate, moles per liter per time, call it seconds, times volume will equal moles per seconds. Volume cancels out, we'll have moles per seconds on both times, it's your batch reactor material balance.
So you can make DNA DT into CA, like, in terms of concentration, by getting rid of the volume on the reactor side, dividing both sides by volume.
Divide both sides by volume.
And then,
So this, you gotta be careful when you do this kind of stuff. You need to check on it though. You can't just throw things and pull things out of integrals or derivatives. You can't just do it. If you're lucky, it might work out. If not, so what do you have? You know that CA equals NA divided by V. So if you want to change, your variable from NA to CA. So you need to rearrange this. NA equals CA times V. DNA dCA will equal V. So DNA equal, yeah, V times dCA. So you can take this guy. We already have it on that side. We have RA times V equals, and we know that DNA equals V dCA, V times dCA dt, and the volumes cancel out.
that got lucky.
Yeah, you gotta do it this way. If you don't do it this way, you're gonna get stuck eventually. You're gonna be missing a negative sign, or even worse, your expression's just not even gonna make sense at all.
Okay.
You gotta do it, if you have a derivative, you have to do a change of variable of this fact time, it'll work out for you. And if you do it a couple times, you know you can do that. You don't have to write this out. You know you can just absorb that volume in there. But you're not really absorbing the volume at all. If you notice, you said that NA equals CA times V. You're pulling a volume out of this and canceling it out with that one. That's really what you're doing. You're not absorbing this volume into the derivative.
No. Like, yeah.
You did it over there. What's up?
So is that the generic mass balance for something, because if you're generating A, you're accumulating moles of A? and
Yeah,
the
because
positive
nothing's
change,
coming
it's
in
gonna
and
be
nothing's coming out.
Positive, versus if you're consuming a negative and then a negative change. So no matter what, it's gonna be positive.
Yeah, it's just generic because you don't know if, I didn't say we were consuming or,
But either way though,
Interesting.
if you're consuming, you have a negative RAB, but then you're changing moles of A is gonna be negative anyway, so you're gonna be
Yeah.
negative.
yeah, I mean, this is the generic version you get to. And then ask yourself, well, what reaction are we doing? Are we doing B going to A or A going to B? If you're doing A going to B, then you know this term right here is gonna be negative. Your change in time has to be positive. This is gonna have to be a negative term. Either throw a negative sign in front of it or say that RA equals negative KCA if it's a first order term. But it's logic. Don't try to memorize anything. Just reason it through. Are you consuming or producing A? Negative or positive rate. And I guarantee you there's gonna be a problem soon where you're gonna have to write some kind of balance where you're writing them for the rate, so you'll have something like A plus B going to C plus D, and you have to write a mass balance, one single mass balance that holds the rates of all these in here, so you're like minus RA plus RB minus RC plus RD. It's gonna drive you nuts if you're trying to memorize the rates, whereas if you just reason through it, you know, just reason through the thing. Also, it depends on what side of the equation you're on. Because if I take this and I say that, say I said DNA dt, generically put plus RA, we have to multiply by volume equals 0. What's the sign of that? If we were consuming A.
Let's see, consuming A, so negative,
This
and that being positive.
is a negative term. That means this term has to be positive, or else it can't be equal to 0. If that's negative and that's negative, you can't get 0. It's just reasoning. This isn't just cookie cutter, oh, let me find an equation to plug into. It's not gonna work for you. It's not gonna work at all. You have to actually think your way through all of these problems. You can't just lean on an equation to solve it before you really think balance. I know all the classes you took. The other class you really had to think was heat transfer, where you truly had to think about the system going on and what equation you're using. For the other ones, for Dr. Tomodax's classes, he gives you equations to design things with. So there's really no thought in terms of how you came up with the equations. You just get these huge equations for pressure and everything else, which is fine. It works for that system. Doesn't really work for this. And if you look through certain textbooks, particularly the one I pointed out to you, the Fogler book, if you use the book improperly, then you're just looking through a book looking for equations that has the same number of variables you're looking for. And you try to plug it in. That's not the way to properly use that book. And that's why Dr. Jennings hates the book so much, because that's the way people use it. Fogler derives every single one of those equations. And if you just pay attention to the derivation, you learn how he derived it. You can apply it to the own systems, to the systems you come up with. But none of this stuff, every single one of these things are going to change for every single equation. Depends on how you want to write it. It's tough. It is a tough class in that regard. But that's why I just look at it as linear algebra and just use logic. Think about a problem before you solve it. Is this increasing or decreasing? Well, if it's decreasing, it's going to have to be negative. Well, I just said both sides are equal to 0. So if this is definitely negative, in that case, this is going to have to be positive. my copyright information right there. You're doing the recording, that is my intellectual property. Mine. You have to cut me a check if you put that stuff on and sell it.
You can get all the $0.
No, let's. Okay, remember what minute are we at right now? So we have like 10 minutes left in the recording. Delete this part out. The rest of the people that can't attend here, find a good, reasonable price. Nothing too elevated. Something they would be willing to pay, and we'll charge them that. And we'll just have to figure out the split. We'll figure it out. I feel like I should have the higher end of the split. I'm just hit the button on and off. But you provide the hardware. I don't know how much that costs. I don't know what my phone.
Well, he already had it, it's not like he bought it for this, so.
Oh.
Good point. Okay.
Wow.
Your block access.
Wow.
Block.
I don't use it up here.
Yeah, that's definitely 80-20. 80-20. 75-25 maybe.
You know, other
Any
people are
questions
gonna
about
read
this?
it.
Don't want to take a couple more minutes. How did you read? You're already turning in. You can't even ask me more
I
questions.
want, but I wanna know, if this works.
Get your
I'll
points.
talk to you
I don't know.
afterwards, since it's more complicated.
I gotta drop immediately. Houston, Florida State, teach a couple ones. So
And I'll see.
you can ask me right now. if you want.
Reactor.
I'll just wait for my window for the red one.
Reactors for someone?
Yeah.
We're gonna go talk about,
Hydration.
significant figures and.
Oh, God.
Let me tell you guys this right now. Do not be those students who look like complete morons when you do your senior design. Because you're gonna go to Excel, you're gonna have Excel solve all these problems, and then when you report things like, I have a heat exchanger. It's priced at $3,126,246.89. Do not be the guy that reports a heat exchanger costing something to the penny. Do not be the person that keeps on going this way. Don't do that. Don't do that. I've read the reports that you guys did for the previous assignments. That happened all the time. Go into Excel. 3.1 million. Something like that. Because you're going to have professionals come by, look at that, and say, there's no way I'm hiring that guy. You can't even report something that costs. If you said you were a millionaire and you just picked up a penny off the ground, I'm a millionaire plus 1 penny. You would never say that. I'm still just a millionaire. Or if you lost a penny, I'm still just a millionaire. I'm not 999,999. You wouldn't say that. Report numbers that make sense. Don't be those people. And I think I'll spend the time to walk around in the spring, and I'm going to point and laugh at you. And I'm going to point out to the judges for sure. Like, oh yeah, they did a good problem. Look how much their heat exchanger costs. They reported it to the millionth of a penny. Because they're after sites. They just think it's them. Don't do